Hello and welcome to Spherical Chicken in a Vacuum. In today's class, we'll be speaking about crystalline lattices and how they influence the properties of the material. This is the last part of the introduction, so we are still in a sort of theoretical background before actually speaking about material science. From the next class, next week, or at some point later this month, we will start to speak about some applications, something that we can actually see with our own eyes and how we can tailor and optimize the properties of a material. So last time we discussed about gold and gold ingots and about how an object like a gold ingot is made of a shape and a material. And we discussed about this, mainly we discussed about the material. And this time, let's imagine that this ingot is actually a rectangle. So we will have a look into dimension. Let's think about how we can put spheres that are like simplified atoms inside of these rectangles. There are basically two ways. There's the ones in which we put spheres on top of each other and they have only one contact point for each sphere. And in this design, there is a sort of big hole in between spheres. And also, the spheres, if you consider gravity, the spheres are a little bit unstable. It's very difficult to put one sphere exactly on top of the other without it slipping on one side or the other. There's another way to sort things out, which is in this form, in which the second line of spheres is in the intermediate position between two spheres of the first line. In this case, the holes, the porosities, the holes between the spheres are much smaller than in the previous case, and if we add the gravity, the condition is more stable. Now, nature is amazing. We know nature, the universe, the laws of physics, whatever you want to call it. But basically, we are playing Tetris here. And if you are familiar with Tetris, we need to try to close all the gaps that is possible. So to put materials as close as possible. And this is a condition that has the minimal requires the minimal energy because nature doesn't want to waste anything. So we have to use the minimum input of energy possible to have a stable condition. Okay. Then, if you play the Tetris as much as I had, there are even Tetrises that have like pieces made of 5 squares instead of 4 squares that are much more complicated. And this is sort of a good example of how things work in real life with atoms because there are so many configurations that combine in different ways. And the more complex is the situation, the more difficult it is to pile up the elements without leaving gaps between them, let's say like that. Okay. Plus you need to consider also that we have charges because we have covalent bonds that can be polar, for example, and polar covalent bonds have charges on their sides, so we can have, like in this example, plus and minus charges, and those can create a repulsive force. So we cannot actually fill all the space because there's no way to put another plus charge close to that charge. This is a oversimplified explanation, but the main points to keep in mind is that we are playing a sort of Tetris with a lot of additional rules to try to find what is the crystalline lattice that fits the better for our material. Okay, so I also try to make very simple two-dimensional examples with these discs. I try to lay down one first layer of discs, then one second, trying to use the configuration that gives the lowest amount of space between the disk lines. This discs, of course, are sort of two-dimensional atoms, and I can move them, the top line, and you can see that the porosity is much bigger than before now, as I explained you before. But if instead of having perfect circles, we have something that is slightly off shape, in this case, it's just 10% longer on one side, so they are egg-shaped instead of circles, then we will see that the porosity in the middle of these egg-shaped atoms is actually bigger. And even if the difference is just 10%, the porosity is much bigger than before. And this is actually a clear example of what happens with the polar covalent bonds because they have a different shape. They don't have not the covalent bond itself, but the atom the electron cloud of the atoms has a different shape, so they cannot line up as before. And as you can see, the center of the disks on the x-axis is the same as before, but on the y-axis they are different. So the basic element is not a perfect square anymore. So if we go from center of circle to center of circle, we can draw small regular squares, but with the oval, with the egg-shaped ones, they are rectangles because one axis, the y-axis, is longer than the x-axis. And this can be translated in three dimensions, of course. And well, I will speak about today. We'll speak about what Auguste Bravet did before me, because he made the models of the 14 main crystallographic structures, crystallographic lattice. There's a lot of different ways to speak about crystallographic lattice. Today's we will only focus on what Bravet did for us. And I don't think we will need to study more in detail, at least not at the beginning. So I think these models will stay with us for a while. Okay, there's no need to go deeper. There's much more to dig in the world of crystallographic structures. So let's start from the three-dimensional basic element, which is a cube. And you can imagine the cube because it's sort of the same model that I drew before, but this time with an additional dimension. And since when the balls are all close together, they are a little difficult to see, let's just make a distance between the centers of the balls, and we can see that there are three sides that are the same length, and there are three angles, and all the angles are 90 degrees. This is a fairly symmetrical and stable structure, but it leaves a lot of holes inside the three-dimensional lattice. So this is called simple cubic, and in reality, in real life applications, I think only polonium as an element as such a structure is very uncommon. Okay, it's very uncommon because there are better way to use space, and one better way to use space is to put another atom in the center. In this case, of course, the lattice gets a little bit larger, okay, but we have one extra atom in the center, and this increases the packing factor to 68%, from 52 to 68. And iron alpha is a good example of BCC, body-centered cubic structure. Then we can remove the atom we put in the center and put one atom in the center of each of the face of the cube. And in this case, we obtain what is called a face-centered cubic structure, which has a packing factor of 74%, which is basically the highest we can get. And examples of these materials with this structure is, I don't know, aluminum. Aluminum is such a good example. So packing factors go from 52 to 74% in the cubic elements. So simple cubics, body-centered cubic and face-centered cubic. And there's no way, no other structure goes over 74%. And we will see. Second one, where A and B are equal, but they are different from C, and the angles are 90 degrees, 90 degrees, and 120 degrees. This is the hexagonal structure. It's a little bit more complicated than the square. We don't really need to waste more time on the description of the structure as a 3D crystal, lattice crystal. Let's speak about the packing factor. It's 74 again. So this is again the highest packing factor that we can achieve, as high as the face-centered cubic we saw before. Then we have the lattices where A equals B and is different from C, and all degrees are 90 degrees. So these are boxes, basically, all boxes that have a square base and a different length for the height. Okay, and in this case we have the simple tetragonal, which is based on just 8 atoms, and the packing factor will always be lower than 52, because as we squeeze this box from the top down, the maximum compression that we can reach is the compression that we have in a simple cubic, which is 52%. Why this happens? Why there is one side which is longer than the others? One example is the polar covalent bonds that we spoke about before, that create a distortion, and so the atoms cannot stay close together as close together as they could before. This is a good example. And there is a variation of this one in which we can put an additional atom in the center. This is similar to the body center cubic. So the maximum packing factor that we can reach in this case is 78%, which is for body center cubic. Again, when A different than B different than C, but the angles are all 90 degrees, this is the most general box of all of them, where the packing factor, again, is less than 52. A, B, and C are different length. So the best we can achieve is the limit situation in which A equal B equal C, and they are so close that their atoms touch each other. This is the best situation we can get, which is, again, simple cubic. We can put something inside of the simple orthorhombic, which, by the way, is the structure also that can we find it like in sulfur. And in the body center and orthorhombic, we have a packing factor of 68 because, again, it's just a stretched body center cubic structure. Again, it's stretched in two directions because there is some forces, electrostatic forces, there's some deformation that we have in the electron orbitals that force the structure that cannot get closer than this. So this is the case limit of the body-centered orthorhombic structure is, again, the body-centered cubic structure that we saw at the beginning. We have one more, which is the face-centered orthorhombic structure, which is the same of the face-centered cubic structure that we saw before, but we just pushed and squeezed our structure so that the three sides of the box have different sizes. Packing factor, again, at top, it can be 74%, which is the limit situation in which it is a face-centered cubic structure. And we get one extra bonus. We have the base-centered orthorhombic structure in which we have only two extra atoms on the top and on the bottom of our box. In this case, the packing factor is slightly little better than the packing factor of the simple orthorhombic. Okay, this is the family. Orthorhombic is the family of lattice structures that have the most types. And then we have something that doesn't change in length, but change in angles. And when A equal B equal C, gamma equal A and equal B, but they're all different than 90 degrees, we have a rhombohedral structure, which can reach a packing factor of 52%. It looks like we just squeezed or pulled our perfectly cubic structure in two opposite corners. So again, the limit situation is the one in which the angles are as close as possible to 90 degrees. So again, simple cubic. We always fall. All these structures are just sort of deformed structures of something we already saw before with the cubic structures. And there's no other type of rhombohedral structure. When the three sides are all different, and gamma is different from alpha. Alpha is equal to beta, and alpha and beta are 90 degrees. What happens is that we have the simple monoclinic structure. That, again, is a distorted version of the simple cubic structure in which we just push the top four atoms slightly on a side compared to the bottom four ones, so we form an angle. The other angles are 90 degrees. Only the angle in which we pushed is different than 90 degrees. And of course, the length of the three sides is different. This is a structure that can be found, for example, in zirconia. So it's not even a weak structure. It can have quite high properties. And also in calcium sulfate, for example. And then this has another structure in the same family, which is the base-centered monoclinic, which has, again, slightly better packing factor that we already saw before for monoclinic base-centered structures. Then we have the most extreme case in which the length of the three bonds on the three sides is different and the three angles are different, and this is triclinic structure. And this this is the example in which everything is basically deformed. We stretched, we squeezed, we pulled. So we have long, different lengths, different angles. And this is the structure that has the least symmetry, is not symmetric at all. And this is the first time I mention symmetry, but this is an important concept because as we go for really extremely symmetrical structures like the cubics, for example, we move, we start to stretch, and we play with the angles of our lattice. We lose the symmetry, and this means that materials that have these structures, like triclinic, for example, like aluminum silicates. Some aluminum silicates are triclinic, have different properties, thermal properties, optical properties, mechanical properties, depending on the angle at which we observe our material. So this means, for example, that aluminum silicates are weaker in one direction respect to the others, or that they have birefringence, so they split light beams that hit the surface. Well, we can go in detail of the optical properties in the future, but optical properties can be also altered as well as mechanical properties, as well as thermal properties, etc., etc. So, which structure is stronger? Which structure is weaker? This is a question that doesn't really have a answer because it really depends also on the elements, on the bond, on the strength of the bond. Some structures are, well, metals like to stay close together. So metals usually have structures with high packing factors, like body center cubic, face center cubic, or hexagonal. Hexagonal is titanium, for example. And with the exception of hexagonal, that is already a bit difficult to deform, these are structures that are tough and can have really high mechanical properties. Also, they achieve high densities, so they can reach good strength. But again, diamond, alumina, zirconia that are in the other lattice families, they also have high properties. So it's very hard to guess the properties of something just by looking at the lattice structure. Some lattices are very uncommon. We saw the simple cubic is sort of not so common in nature, and the triclinic is also not so common in nature. Some other are more common, but it's not just about the lattice structure. It's also about the strength of the bonding. It's also about the environmental situation, like the temperature, or also about what really we meant when we mention strength. Is it toughness? Is it hardness? Is it whatever? It's material science is complicated. Science, material science is very complicated, but the basic elements that form most of the crystalline structure that we can find in everyday life fall in this situation. For example, tetragonal phase. We spoke about iron as cubic, body centered cubic, but martensite, which is one special structure, metastable structure of steel, it's actually a tetragonal lattice, which is hard and brittle. So yes, modifying the lattice structure changes the properties, changes the symmetry. So as you modify the angles of the structure and we stretch the structure, we lose symmetry. So the material gets stronger in one direction and weaker in the other directions. But we have properties that change. But overall, it's impossible to say which structure is stronger and which structure is weaker, because every structure and every type of bonding has is weak points and strong points depending on the application we are thinking. And I think this is more than enough for today, and we will see again in the next class. Bye. Hello and welcome to Spherical Chicken in a Vacuum.